Alright folks, nice and easy, a nice and straightforward video lesson today. I am obviously hoping that this is the last one that we're going through in this course, but we're taking it one at a time. This one should be pretty straightforward for us. We'll start off with what we call our Pythagorean identity, and that's another trig identity that we can add to our growing list of identities we've discovered in this chapter. Obviously, we started with our related acute identities and our cofunction identities, along with our compound angle identities that we discovered yesterday. Now, if we're working here, we're working on a unit circle, and if it's a unit circle, we know that means the radius is equal to 1. And we'll consider one point along our unit circle. We can consider this at the coordinates x, y, where we know x is equal to the sine of theta, and y, whoops, these are in backwards, x is equal to the cosine of theta. Glad we spotted that. And y is equal to the sine of theta. Fantastic. Now, if that's the case, okay, so we have a radius here, our terminal arm. Let's go with something like that. Our terminal arm, we know the radius is equal to 1. And I know then if I make a little triangle here, first of all, my theta is inside my interior angle of the triangle. My x-coordinate of my point, xy, can be given by this. My y-coordinate can be given by this side right here. Now, if that's the case, okay, well, this is a right-angled triangle. And since it's a right-angled triangle, I know the Pythagorean theorem holds true. So I know that x squared plus y squared is going to be equal to r squared. Well, in this particular case, I know my radius is equal to 1. So that's equal to 1 squared, that's equal to 1. So x squared plus y squared equals 1. Good. Now I also know that x is equal to the cosine of theta. So that means I'm not just working with x squared plus y squared, I'm working with the cosine of theta squared plus y, which is equal to the sine of theta squared, and that is equal to 1. And then I can simplify that further just using our new notation, how we're getting used to writing the square of the cosine of theta. That is the cosine squared of theta plus the sine squared of theta is equal to 1. There we have it, our Pythagorean identity. Now, if you would like, you can copy this down on some scrap paper beside or on the side of the note, but that is an identity that we're going to be using as we work through finding our compound angle formulas. Now let's consider here, okay, we already know our compound angle formulas from yesterday, and that is I have chosen two of those formulas. I believe we numbered those numbers 1 and 3 on our note from yesterday. Now, if we consider for one moment, if x is equal to y, and that means really if the value of y happens to be the same as the value for x. Well, if that's the case, then I could rewrite my compound angle formulas, and I could rewrite them, replacing the y's with x's. So I'm substituting in my x in place of y, so that means I'm working with the sine of x plus x is equal to the sine of x times the cosine of x plus the cosine of x times the sine of x, where again, this second line, this line in a light blue color, is purely copied from line 1, substituted in the value x for x. Now, x for y. Now we can simplify this a little bit further. Okay, so the sine of x plus x. Well, really that's the sine of 2x. Okay, so if I'm working with the sine of 2x, that's going to be equal to the sine of x times the cosine of x plus the cosine of x times the sine of x. Well, I know when I'm working with multiplication that order does not matter. So I could rewrite this if I wanted to as the sine of x times the cosine of x plus the sine of x times the cosine of x. Well, hang on, that's the same term there twice, so I could rewrite that as 2 times the sine of x cosine of x. And this right here, sine of 2x is equal to 2 times the sine of x times the cosine of x. This equation right here is one of our new, what we call double angle formulas. So we'll call this, I'm going to use a new color here, this will be equation 1 on this note here. Now, if that's the case, we can follow the same logic that we just used on our equation 3 from yesterday, and that is our cosine equation. Now I'm just going to move this down so it doesn't overlap with my other work, but we'll work in green over here, where the cosine of x plus y is equal to the cosine of x times the cosine of y minus the sine of x times the sine of y. And again, we can substitute in, we can take out any of these y's, and we can substitute in x. So again, we're considering, okay, this would be our equation from yesterday if under the special circumstance where y is equal to x. So I'd be left with the cosine of x plus x is equal to the cosine of x times the cosine of x minus the sine of x times the sine of x. And again, I can simplify this further. Okay, let's zoom in a little more. I can simplify this further. I'm working with the cosine of 2x is going to be equal to cosine of x times the cosine of x. Well, that's like the cosine of x squared minus the sine of x times the sine of x, and that's like the sine of x squared. And again, I can rewrite this using our new notation. That is the cosine squared of x minus the sine squared of x. That's equal to the cosine of 2x. And here we have our second double angle formula. Fantastic. Now we might notice something about this second double angle formula, and it's about the terms. We notice the term cosine of x squared and the sine of x squared. Where have we seen those two terms before? That's right, from our Pythagorean identity. So if I copy this Pythagorean identity over here, and you know what, we'll put it right off to the side right here, then I should be able to rearrange this equation so that I can isolate for either of these two terms down here. That is, I can isolate for the cosine of x or the sine of x. So if I try here, okay, I could subtract the sine squared of theta from both sides and work with the cosine squared of theta is equal to 1 minus the sine squared of theta, okay? Or from this first equation, I could subtract the cosine squared of theta from both sides, working with the sine squared of theta is equal to 1 minus the cosine squared of theta. All right, now that means what I could do to rearrange equation 2 down here is I could substitute in either of these values for the cosine squared of theta or the sine squared of theta. We'll work first and we'll substitute in for the sine squared of x. Now notice, yes, these are both using different variables, but it just really depends on where we're coming from for these variables. Either way, they are interchangeable at this point. So I can work here. I'll change my color for this right-hand side here, okay? So I can substitute in I don't know, we'll call it, I'll call it 2a and 2b. So I can sub in 2b, sorry folks, I'm jumping all over the place, that's okay. I'm substituting in 2b to this above equation, so I'd be working with the cosine of 2x is equal to the cosine squared of x minus, and here's where my substitution comes in, rather than the sine squared of x, I'm working with 1 minus the cosine squared of x. And you might say, okay, well, hang on, I could distribute this negative sign, and I might notice that I have the cosine squared of x term there twice. So I'm working here, okay, so this is going to be equal to the cosine squared of x minus 1 plus the cosine squared of x, and that's equal to 2 times the cosine squared of x minus 1. Fantastic. This is equation 3. This is another double angle formula. It's just another form of our second one that we found. And then we can perform that same step of operations, but rather than substituting into b, we'll substitute into a. We'll sub in 2a into equation 2, sub 2a into equation 2, and that should leave us with down here, all right, the cosine of 2x is equal to the 1 minus the sine squared of x minus the sine squared of x. And I can simplify that using the same method that I used before, working with 1 minus 2 times the sine squared of x. And there we have it, our fourth double angle formula. Again, double angle formula 3 and 4 are just two different forms that we already found from equation 2. Now, these allow us to write, if we're looking at equations 3 and 4, we have here an equation purely in terms of the cosine of x, and an equation, at least on the right side, in terms of the sine of x. So that should lead us forward. Now I will include on, let me see here, we can go through a similar process with our tangent of 2x equation. So I'm working here, okay, so my tangent of 2x, and this is straight from the note yesterday, from the 7.2 note. The tangent of, x plus y is equal to the tangent of x plus the tangent of y, all divided by 1 minus the tangent of x times the tangent of y. And that is if x equals y again, then we're working with the tangent of x plus x, which is equal to the tangent of x plus the tangent of x, divided by 1 minus the tangent of x times the tangent of x. And using the same logic we've used before, then I'm working with the tangent of 2x is equal to tangent of x plus the tangent of x, so that's 2 times the tangent of x, all divided by 1 minus the tangent squared of x. And here we have it, double angle formula 5. Now, what I would like you to do as we work through these examples down here, and you know what, I'll try and update this, this note to give you a little bit more space for copying all of this extra work there. But we'll work through example 1 in this note, and I know I've already uploaded another video for example 2. So example 1, we're working here, I have the cosine squared of 5 pi over 12 minus the sine squared of 5 pi over 12. And hopefully we recognize this form. Okay, well this is like the cosine of something, cosine squared of something, minus the sine squared of that exact same angle. Okay, well do I have any formulas, any identities that can help me out here with the cosine squared of something minus the sine squared of something? And absolutely, if I look up at my new equations, I see it in identity 2. I'm working with, again, the cosine squared, the cosine of 2x is equal to the cosine squared of x minus the sine squared of x. So that means I should be able to substitute in, this is going to be equal to the cosine of 2x. Well, what's x in this case? We're working with 5 pi over 12. So that is, we're using this new identity to rewrite or to write an equivalent expression that hopefully we will be able to evaluate. So here, if I'm working with 2 times 5 pi over 12, well, hang on, that's like the cosine of 10 pi over 12. What's 10 pi over 12? Oh, that's just 5 pi over 6. Just going to write that in one line here, 5 pi over 6. You know how to evaluate the cosine of 5 pi over 6. You use your cast rule, then you use your special triangles. So we'll use our cast rule, nice and easy, CAST, 5 pi over 6. I'm working with a terminal arm in quadrant 2. And I know my sine ratio is positive in quadrant 2, so cosine is negative. So I'm working here with the negative, the cosine of my related acute angle. My related acute angle in a case like this is pi over 6. So negative the cosine of pi over 6, and I should be able to finish that off with a special triangle. I have pi over 6 in my top angle, pi over 3 down here, 2, 1, root 3. Okay, so the cosine of pi over 6 is going to be equal to my adjacent side over my hypotenuse, and that is root 3 over 2. So negative the cosine of pi over 6, I'm working with negative root 3 over 2. Fantastic. So we should be able to follow the same kind of a pattern for example 1b. I'm not going to solve all of example 1b, but we will go through it a little bit here. So again, we're trying to recognize, okay, so if I have 2 times the sine of an angle times the cosine of that same angle, then really what I'm working with is something like 2 times the sine of x times the cosine of x. So I'm asking myself, okay, do I see that in any of my work up here? And yes, I do. I see this in equation 1, identity 1, 2 times the sine of x times the cosine of x. So now I know that that's going to be equal to the sine of 2x. So I can rewrite that down here where my x is equal to pi over 8. So I'm working with the sine of 2 times pi over 8. Well, 2 times pi over 8, I know how to handle something like that. That's the sine of pi over 4. And all of a sudden, the sine of pi over 4, that's something you know how to evaluate using your cast rule, using your special triangles. So I'll ask you to finish that one off, and I'll move on to example C. 1C. 1B, that full solution will be available on the note uploaded to the classroom. And the last example we'll go over here, 1C. Okay, so this one looks a little bit more challenging off the start, right? Because I see 4 times the cosine squared of x. Okay, so negative 4 times the cosine squared of some angle, we'll call it x, plus 2. And I might say, well, hang on, I don't see this piece involved in any of my new formulas up here. It's not in equation 1, it's not in equation 2, it's not in equation 3, or in equation 4. And you're absolutely right, it doesn't show up there. But we know how to evaluate, or rather come up with an equivalent expression of this right away using our grade 10 factoring skills. I could common factor this a little bit, so I could common factor a negative 2. So negative 2, okay, so negative 2 times the cosine squared of 7 pi over 12 minus 1. And that's the key. Okay, so now this piece here can be written as the cosine squared of x minus 1. Do I see that involved in any of my equations up here? Absolutely, yes, I do. I'm working here the 2 times the cosine squared of x minus 1. So I know that this is equal to the cosine of 2x. So I can rewrite this down here. And actually, I'll move this over. You know what? I'll leave it. This is going to be equal to negative 2 times the cosine of 2x, where x is equal to 7 pi over 12. So 2 times 7 pi over 12. Fantastic. Whoops, minus 1. And all of a sudden, we're solving this problem just as we've solved the previous one. So negative 2 times the cosine of 7 pi over 6 minus 1. And we should be able to evaluate this, again, using our cast rule and then using our special triangle. So try it out. The full solution will be uploaded on the classroom. And like I said, I will have the second video linked to example 2 on the second page here.